Okay, today we're going to go over the electric potential of a continuous charge distribution. Of course, when we say the word continuous, you know what that means. It means there's an integral coming. So, thank you, Sean. Okay, yeah. Just identifying that was Shun with the outburst. All right, so we need to review the potential of a point charge. Start with, and then examples of other continuous charge distributions. So we're going to start with the point charge. All right, remember that if we'll have a Q1 here. It's got some positive charge, and then we'll have a Q2. It's got some negative to it. And another charge over here, let's call that Q3. Okay, the potential for any one of these, because it is a scalar, it matters not from which direction, okay, is causing the potential. Okay, and for Q2 here, its potential, okay, is equal to K, okay, Q over R. All right, and this is the measure of work it takes to push this charge, okay, through our to this location per unit charge. Okay, so how much does it take to push this unit into, to get it into this position per unit charge? Okay, and so if we have multiple charges here, then we find that our voltage for any one of them winds up being okay, the sum of all of our individual ones. So it's going to be K, QI over RI. All right, so what if we have, this is just for point charge, but then what if we have, and what if we have our amoeba here? What if we have our amorphous shape? Okay, which for some reason my amorphous shapes always seem to look the same. I always seem to make 3 lobes, but anyways, and this has a all right, and so anywhere on this thing we may have a DQ. I don't mean a Dairy Queen. Yes, or a disqualification. Okay, so we take this little area right here and we call this DQ. All right, and we have a point off in space over here. Okay, this is our test charge. Okay. The work it takes to get here, based on that little point, just on this DQ, okay, is wrong pen. There we go. Is K DQ over R, right? For just that one particular spot. The potential it takes to get here, just based on this one little charge, gives us that. Yeah? All right. Yes, and so as if we add all of them up, the way we add all of them up is by integrating, okay, for all of our DQ, and that's going to, this is what our volume, not our volume, our potential equals for this particular charge distribution. All right. So we're going to practice some other ones. Okay, that we have this uniform, this continuous charge distribution. So the first one we're going to do is we're going to be given we're going to do a ring. Now our ring is going to be okay. This is just for a ring charge. Given. That's why I said given when I wrote it. Yes, it says given. All right. And then along its so here's our radius, by the way. Okay, so this is a ring, and we're kind of looking at it with perspective here. All right, and along our ring we have charge. All the way around our circular ring. Remember, we're looking at this in perspective. Those are negative charges. Dun dun dun. That's right. Okay. And we want to find, we are at a spot right here that is a distance x. Okay, it is a distance x from the plane of the ring. Okay, along the axis of the ring. You follow me here? We are on the axis of the ring, and okay, distance x away. That is our point P. All right, we want to find the potential and the electric field. All right, so we're going to solve now. That says solve, Sean. Okay. Okay, that says solve. All right. Now, our voltage equals the integral of K dq over R. No, R. K dq over R. Yeah. Okay. Now, for any particular dq, it's this little segment on the ring, and it's going to be the same for all of them. So, P is what distance away from here? Well, that is okay. Right. So this distance is the square root of r squared plus x squared, or x squared plus r squared, depending on your preference. Okay. You may see where this is coming from. Okay. Well, actually, sort of. This is nice because this never changes, right? X squared plus r squared is constant. As we go around the circle, it's a constant. So, okay, so this is going to equal K over x squared plus r squared. Integral of dq, but the integral of dq is just q. So this would be our potential at this point from the ring. Okay, but we also have to solve for E. And so let's solve for E. Okay, you are allowed to do this on your test. Question? No. Okay, Nick, you just look poised to answer one, or to ask one. Okay. Yeah. You're allowed to do this on your test. Do you guys remember the gradient? Yeah. Okay. There's only one direction here. Okay, and our potential field equals negative the gradient of our potential. Which is equal to negative partial voltage over partial x I hat. This is how we develop our vector from our scalar quantity potential. Yeah? All right. So, there's good news for this. Okay, because this is only happening in one direction. Okay? We're only concerned about the one direction. So, EX is going to equal negative d dx of this bad boy. So this is kq times, I don't want the square root there, sorry. No square root, forget square root. X squared plus a squared to the negative 1/2, and I just want to write it like that because I don't want to bother with quotient rule. All right? And so this becomes, this negative 1/2 is eventually going to make a positive out here, so we're going to get a kq. In fact, let's do this. kq negative 1/2 times x squared plus a squared to the negative 3/2 times the derivative of the inside, 2x, I hat. That negative cancels with that negative, and we are left with k, q, x, because this 2 also cancels with that 2, x squared plus a squared to the 3/2 I hat. And that would be the field at that point. Oh, because I wrote A in my notes, not R. Was that what you're asking? Yeah. A, yeah. Sorry. A equals R. My bad. R. Okay. Now, question, Nick. Guys. Nick?
Okay, is x and r considered constants then, not variables?
Are they? Up here are x and r constants in this particular situation.
So they are constants.
Yeah, I mean, they are constants in so much that once you establish what they are, they don't change in the problem. Okay?
That's why you pulled out the integral?
Yes.
Okay.
Yes.
Thanks.
Did you have to do the gradients, or could you just do
No, you could very easily have just done
regular?
just the regular derivative.
If there was a y component, I didn't have to do that.
Right. If you do the y component, then you throw the gradient in there, and right. Okay. Lucky for you guys, it's not going to happen on your test. So, okay. New one. Okay. This time we have a rod of length L. We have a rod of length L, and we have a point that is the distance A above one end. Okay, and the distance from the rod is the width of the rod is negligible compared to the distance A. Just gotta say it, because otherwise it makes it a really nasty math problem. But okay, so the size of this is negligible compared to the size of A. Follow me there? Okay. All right, along this we have positive charges. All right, so this is our given. That says given, Shun. Okay. We want to find our voltage. at A. All right. So we're going to solve. All right, now we have some interesting things happening here. What I'm going to suggest to you guys is that you draw a an axis like so. And although it doesn't look like it really is, that those should be perpendicular. All right, and then we have right in here a DL, which is the length, or a DQ, depending on how you want to call it. Let's call it DQ. Okay, DQ is our portion of charge right here. Okay, but how are we going to define DQ? If this whole thing has a charge of Q, all right, then DQ is going to equal Q over L DL, right? Or DX. Sorry, we'll call it DX. Okay, that our change in our charge is going to be our linear charge density times dx, right? Because we have uniform charge. Okay. All right, so our voltage over R, and we pull out our constants. This is going to be K Q over L. I'm skipping a little bit of a step here. Integral of dx. But what's our R? Our R. Okay, our distance here. Okay.
A squared plus L squared.
Oh, it's A sine
ADL. Oh, yeah.
Okay, our distance is square root of. Okay, if this is in units of dx, and this is going, then this would be x, right? Okay, that's our x. This is going to be x squared plus a squared again, right? All right, but x is now a variable. So we can't just pull it out of the integral. This is square root of x squared plus a squared. This is nasty. Which is why, I don't know if you've noticed, but you have some calculus stuff in your on your green sheets, if you guys have kept those. And I don't remember what page it was.
Isn't that an inverse trait?
What's that?
Well, it's tan.
No, it's not. If you give it
It's an A over X equal to A tan
Do
theta.
you guys remember what this is? Because I don't remember what it is.
X equal to A tan theta.
I don't want to do that.
I got it.
We'll do it anyway.
Oh, that thing?
Yeah, she's like, oh man.
So
Yeah.
what I would do is I would go look up my table of integrals.
Yeah, because you get on the tech.
Okay, you should have them.
Table of integrals.
You have a table of integrals on the test.
Really? Somewhere in your
Okay, and I will just tell you that it is. Okay, look this up.
Oh, wait. Oh, I forgot.
Okay, this is and I'm sorry, and this goes from 0 to L, because that's the length of the rod. I need to include that. Okay, this equals KQ over L, okay, times, and here it is, it's ln x plus square root of x squared plus a squared. I hate saying natural log, so I call it ln.
And you don't say LN.
I don't say ln, I say ln.
Jeremy Lin. Because there's already
Okay, from 0 to L. This is our integral. Okay, so now we have some manipulation to do. We start throwing the L's in there, we start throwing the zeros in there, and we get KQ over L times the natural log of L plus that did sound kind of creepy. Okay, if we plug 0 in there, there's a 0 there, there's a 0 there, it's square root of A, that'd be 0, and there would be A. So natural log of A. Then, using our log rules, that we're going to get KQ over L. Yes, but lambda is a temporary variable. It's not one of the quantities. Yeah. Oh, not len, sorry. L plus square root of L squared plus A squared all over A. Okay, and that's it. Now, you get a table of integrals on your test. You're welcome to use it. Okay, so that you don't have to derive all of this junk on your own. All right.
So we can look it up on our
Hey, Mr. Allen, what's inside of the parentheses?
Here?
Yeah.
It's just L plus.
L plus.
It's this quantity. Well, we did the log rule, so it's this quantity divided by A from up here, right? I should have put a parentheses right there.
L squared plus A squared?
L plus square root of L squared plus A squared all over A. All right. Okay, which brings us to the potential of a charged conductor. Okay, so now we're sort of on to part two of the lecture here. Please remember that everything we've talked about so far, all of our charged situations, are under electrostatic conditions. That the charges are not moving. If they are moving, then we're dealing with current. Okay? And then we start dealing with electromotive forces. But we're not there yet, so we'll start talking about current and resistance and all that sort of stuff later.
I remember you answered before, but I forgot. What's insulator mean when something's insulated?
If you have a charged insulated insulator. I'm waiting for. A charged insulator means that the charge is distributed evenly throughout the object, as opposed to a conductor. If it's a charged conductor, it is only on the surface. Okay, which is what we're dealing with here. Okay, if we have a charged conductor, electrostatic condition means that there is no flow of charge. Okay, and when we get to flow of charge, we'll start talking about current. But once we start talking about current, then we start talking about how moving charges induce magnetic fields, and which is really cool stuff. And we'll get there in a bit. Okay, so here we have a charged. For a moment, we have a sphere, a conducting sphere that has charges throughout. I'm not sure I explained this well last time, so I'm going to try and do a little better job this time. These charges are throughout the conductor. If somehow because remember, our charges come from our fundamental particle, which is the electron, right? Okay, it's the electron, actually has a charge. This is the fundamental unit of charge, is the electron or the proton. This has a value of 1.6 times 10 to the negative 19th coulombs. What's that?
Are we going to be given that on test?
Yeah, that's on the test. Yeah. Okay, a proton is a positive 1.6 times 10 to the negative 19th charge. Luckily so, because the two of them make things electrically neutral when you have equal numbers of protons and electrons. Like in an atom, you have, by definition, you have equal numbers of electrons and protons. When you have a charged object, okay, you either are putting electrons on it or you have taken electrons from it. Okay, so keep in mind that that's the case. We often talk about charged particles, like positively charged particles, as things that move themselves. Okay, what actually happens is the charge itself redistributes, okay, rather than the atoms themselves necessarily moving. You follow? Like electrons move, particularly in conductors. The electrons are free to move throughout your metal. Because they're free to move, it is the electrons themselves that redistribute, okay, so that the abundance of your imbalance is on the surface of your object. So if you have more electrons, the electrons push themselves away because they repel each other. And they push each other as far apart as possible to get to the out. And the only way they can do this is by pushing away to the outermost portion of your object. If you have a lack of electrons, then you have an abundance of positive charge, and the electrons will redistribute within the charged within your charged object to arrange for the imbalance of electrons for the lack of electrons to be on the outside of the sphere rather than the outside of the object rather than the inside of the object. Okay, just how it works, because there is more positive charge. It is a positively charged. The protons themselves don't move. The electrons redistribute to allow the positive charge to be. Because there's more of it. There are fewer electrons than protons in your object. So okay, so the positive charge redistribute. Okay, so. If we have these positive charges, then these don't want to be near each other. There is a momentary flow, just long enough for the charges to distribute to the outside of your object, but not long enough for us to actually call it a current. Okay, it just happens real quick. So these will all push out. To get away from each other, and the way these charges get further away from each other is by residing on the surface of the object. All right, so if we get our charged object, okay, all our charge distributes on the surface, and not only that, regardless of the shape of your object. In fact, let's draw a oddly shaped object. Our charges will distribute. Okay, we're going to get much more into the exact mechanics of how they distribute on this. But they distribute so that the surface of the conductor, this is an important concept here, the surface of your conductor is an equipotential surface. So think logically here. Would it make sense for any one part of our surface to have a higher potential than any other part of our surface? Okay, if the charges are distributing evenly so that they're as far apart from each other as possible, the potential to be at that point is the same regardless of your charge, regardless of where you are. Ashmeet, then Justin.
What does that do with the field lines and the oddly shaped?
Good. For the oddly shaped one, it does odd, and that's coming up. It does. What's that?
Do they like the field lines for the sphere? The potential will be the same like in the circle.
Yes.
For that one, would they look like that?
It will.
Yeah. Right.
It will. It's going to be really hard for me to demonstrate using this particular object that I drew, okay? because way up in here, way up in this piece, okay? Way up in here, okay? The field lines still don't cross, even though it's really hard to draw them otherwise. Okay, so yes, they would be in there, and they'd all colliding towards each other and coming out. Okay, I'm going to draw a teardrop here in a second. This is actually a really interesting discussion. All right, Justin.
You said how the potential is the same because the charges are equally distributed throughout the sides.
Yes.
What if it's like, or outside the outside?
Yes.
The surface. What if it's like, what if the shape you have is like really steeply concave at one point? Would it still be the same? Like what I'm saying, like
The surface will still be an equipotential surface.
okay.
The lines still behave accordingly, and when I draw the teardrop, we'll really start to show how this works. Okay, we know that our voltage or actually this has to be this way. Okay, so I really want you guys to think through the logic here. It has to be an equipotential surface. Because for an object, if we haven't, I really can't think of an easier way to explain it than it would make no sense on a conducting surface for there to be a concentration of charge in one place over another. Okay, now, I'm sorry, a concentration in potential over one place over another, because it doesn't make sense for that. They're going to try and get it as far apart as possible, and that's otherwise we have an abundance of potential energy.
If we assume there was like a denser point of charge, you just let the system go, or just put itself into equilibrium.
Yes, that's essentially what's happening. Is it's finding a charge distribution equilibrium.
Is there like another equilibrium?
That is there,
Well, like the tops of the spheres are denser, and then
What's the top?
you're stealing my thunder. We're getting there. Okay, here comes the thunder. Yeah. Here comes the thunder. Here comes the rain. All right. Falling on my head like a memory. Falling on my head like a deep emotion. Okay, so we know that our voltage equals negative integral of the field times ds. Okay, now here's the cool thing. On our surface, the field is always perpendicular to our change in path. If we move along the surface, we are moving on a differential level. If we move along the surface, we are moving perpendicular to the field line that's shooting out. Yeah? Therefore, any dot product with two things that are perpendicular is dot product
zero.
is 0. Cosine of 0 is 0. That's what I said, 90. Yep, that's okay. All right, no, I forgive you. It's all right.
Also, my eyes.
Yes, yes. All right. So here's a fun explanation. In fact, Faraday and Ben Franklin actually, it was not Faraday, it was Ben Franklin that actually came up with a lot of, in the early days of electricity. Mind you, all of this stuff that we were talking about, all these integrals, it was all discovered before we knew what the fundamental charge was, before we knew that an electron was what carried the charge. And so electrons and protons carried the charge. All this stuff was figured out before then, just through distributions and logic like this. But what was often debated and what Ben Franklin finally settled the debate on was, I drew it great in my notes. Let's see if I can draw another one here. Was something with the teardrop shape. Okay, so we can pretty easily distribute charge this makes sense down here, right? But the reason charge gets distributed is because there are other charges pushing it away, right? So as we get closer to the tip, there are fewer things pushing it away, right? As we continue along the surface. So the charge actually gets denser as we get to the tip. All right, as we get to the tip. Now, I don't want to talk about the differentiability of our teardrop at our point. Yes, it's a singularity. Don't worry about it. Okay, because it's not that important. What does happen, think about the field lines. It's not that important. It's not. The field lines, as we approach this point, start doing what? We've got a lot of field lines. Right? The point is, up here, the field lines at this point are very sparse. The field lines at this point are very sparse. So the potential it takes to bring something into here is very low, right? To bring your positive test charge into here, it's going to be very low. Out here, much denser at this end, yeah? I'm sorry? Than in this area up here. Okay, because as we go to the point, all the field lines are out this way, and there's not much. Okay, so the argument was, and this is, you may start seeing a correlation. You know why Ben Franklin was such a such a mensch was the argument was for lightning rods. How to protect buildings and how to protect structures and well, frankly, people from lightning as they walk through town. Okay, and the argument was: do we want a lightning rod, a conductor on top of our building that looks like that, or do we want a conductor on the top of our building that looks like that? Or what do you think would be more effective at attracting the lightning? Well, if this is pushing off. If this is the electric field, okay, for our lightning rod, as opposed to that, what do you think is going to be easier to push a charge down on? Okay, but of course lightning doesn't make sound. It just goes.
If you get struck, you can make sound.
And it's the air that makes the sound. Yes?
So, since a real lightning rod is not a singularity, doesn't that mean there's have a really high charge density there since it's rounded off, not poison?
No. No, it's not a very high charge density at that point.
No, I mean like the real
No.
ones would be first. So,
Not worried about charge density. Yes, the charge density would be higher. However, because the surface is curving faster, the field to get into that is lower.
Oh, okay.
Okay, so on the teardrop, the charge density at the tip is greater, but
Yes.
the electric field lines are less dense.
Well, these electric field lines in here, to come in from the side,
Yeah.
it's going to be pretty rough.
Okay.
Okay, to come into the tip, it's smooth sailing. Yeah,
They're like the resistance.
yeah, yeah. But there's a point. I mean, we start talking about end effects, but even so, it's still opening up.
Why isn't there like field line on top going upwards?
The entrance.
What's that?
Why isn't there field line at the top? Like
Yeah.
at the very end tip?
There are some,
But they're not as dense.
but it's like one.
Yeah.
It's like one because you only have because the surface. Shh. You know, like, it's important we talk about that. The surface. The field line is perpendicular to ds, right? So here's our d surface, right? Our ds on the tip of the teardrop changes so quickly, right? That this is a real object. Therefore, there is no singularity, right? Singularities don't exist in real life. Okay, unless we're talking about black holes or you know the beginning of time or something like that. So but if you can make your teardrop, then in real life, and particularly at the atomic scale, there is no singularity there. There's just a ds. Okay, but it changes so quickly that the flux from that tip is very small. You know, so the field density, right, is very small through coming out that tip, and that's why the field up here is almost zero or is very weak.
So just think of it as being like since lighting is negative charge, that it goes more towards the more densely positive charge tip of them. Is that not what you want?
I don't understand your question.
Because since the top is has higher charge density, with lightning, which is a negative, be attracted to that part more than the less dense.
Yes.
That's another way of thinking about it.
Yeah, that's an excellent way of thinking about it. Okay. These are all positives, right? What is a negative charge going to do?
Rush.
Okay. If a negative charge is right up above, it's not going to want to do a whole lot, right? But if it's off center, wait, it's gonna slam into the, think about the potential that a negative, holding a negative charge out here would be, right? Would it break it? No. No.
Wait, the teardrop is liquid.
It would dry it.
No, this is a charged conductor with it in a teardrop shape.
I think it was water the whole time. Tuning up a lot of it.
Okay. Now, I can imagine that may have. Now, however, that being said, water is a conducting material.
Yeah, that's what I said.
Okay, and it just does not conduct as well as metals. But okay, so the idea with the negative charge is if a lightning comes in, if a lightning bolt comes in from the side, it's gonna.
I want to see how it.
I want to. If we have lightning come in from the side, it's going to come right in here. Okay, and
Not the tip.
well, no. What do you think the chances are that a bolt of lightning is going to go just like that?
If there's nothing to try.
Because then
Okay, pretty slim, right? But okay, and not only that, but think about this. Shh, hold on. Think about the electrons that are being transferred, right? Okay, you have this potential, and it's electrons that are being transferred between the two. It's all going to happen from the side, and it's just it'll even create more of a charge density up here as your lightning conditions increase. Okay, and it's going to create from the side of your teardrop. That's where you're going to get your major attraction.
What did you say was easier to come to top to the
Well, it depends on the charge you're electing,
Yeah, if you had a positive
Well-
charge.
but it's electrical, so.
Right. It's
So what's coming through the top?
Okay.
You drew the arrow. I mean,
a positively charged, a positive exchange would come right through here. A negative exchange would be, because it would be easy for it to come in, right? A negative could come in through the side. Either way, you don't want to touch it when it gets hit by lightning. Justin.
So, since this is a conductor, the charges are equally distributed at the surface, correct?
Yes.
Then since
No.
there's more surface per
It creates an equipotential surface. They are not evenly distributed. They creates an equal potential surface.
so they're not equally
So the
distributed. It's just
No.
potential's always equal.
potential's always equal.
Charge density is not constant.
Okay. Does it have to be like a symmetrical shape? Okay, wait,
The math gets really freaking hard if it's not a symmetrical shape.
this is what I was thinking.
Well, it's radially. Okay, time out.
Symmetrical.
Time out. This is the end of the lecture.